Right, folks, let's continue. We have learned in the previous lecture to build Taylor series approximations for functions, but at the very end we've observed a strange phenomenon for the series that we have built for the log. If we are to plot the higher and higher levels of approximation, that's x equals 1, and this is 2x. Then the log itself behaves as a logarithm should. It crosses the 0 at 1 and then slowly grows. When we built the order 1 Taylor series, it was just a tangent line that touched our log at the reference point and then departed from it. And around the reference point, the accuracy was plausible. Then we plotted a quadratic curve. It was a bit closer. Then we plotted the cubic curve, but we started to see that around x equals 2, actually there is no improvement that the cubic curve, although it comes closer to the log everywhere else, around 2 started diverging. And then if we plotted x up to x to the 4th, the Taylor series, we would see an even greater divergence around that point. So something strange was happening around x equals 2, where the series that was getting more and more accurate and closer to our real curve, somewhere near the reference point, was misbehaving around 2 and further. And if you plot this closer and closer to 0, you will predictably find that as the log goes to -infinity, this series starts deviating from it more and more, because, well, simply a polynomial cannot go to infinity. What is going on? This is something that in mathematics is called a convergence problem, and let us remind ourselves what the series had been. Our log was a sum m equals 1 to infinity minus 1 to the power n plus 1 over n, and then x minus 1 over n. Let us think about what can go wrong in such a construct. Generally speaking, it is a sum over n of some terms bn. That could be, as you can see, very complicated. Well, these terms necessarily, because our sum is from a certain number all the way to infinity, these terms have to reduce, right? So we must have the limit n going to infinity of bn actually being equal to 0. Otherwise, this sum will keep going and going and going, and we would never be able to actually terminate it or finish, because we would never arrive at a situation where the accuracy has become sufficient. So this must be true for the series to converge. But not only must this be true, the limit has to be achieved fast enough. Because on the one hand, these numbers are going to 0, but on the other, we still have an infinite number of terms. And so not only must this be true, this must be happening quickly enough. For that sum to actually achieve a finite value. A good example of a series that satisfies the first condition but doesn't satisfy the second is, for example, 1 over root n. If we start evaluating this on a computer, even though the limit of each individual term is 0 as n goes to infinity, there are so many of these terms that this sum actually is infinite. However, if we plot something like this, if we calculate something like this on a computer, 1 over squared, I don't remember what this converges to, something that involves pi, but this is less than infinity, this is finite, it's a number. So there are clearly series that do converge and series that do not converge, and there are series that converge at some points, but then perhaps not others. And so our objective today is to look at the ways of finding out whether a particular Taylor series converges, first of all, and second, to find out where it is convergent. And the interval in which the Taylor series does converge is called convergence radius, and this is our first topic today. Convergence radii. The criteria that I'm about to give you, I will not derive because we don't have sufficient time in this course. Derivations exist, you can look them up in the mathematics literature, but the simplest criterion that we have for whether something converges or not is called ratio test. And it is as follows: a series sum n equals 1 to infinity n converges if the limit n going to infinity of the next term, so bn plus 1, over the previous term, bn, is less than 1. What this means is that asymptotically, as we go further and further in n, further and further down in that series, the next term has to be smaller than the previous. If that is true, then the series converges. And then diverges if the limit n going to infinity, bn plus 1 modulus over bn is greater than 1. Well, this is also fairly obvious intuitively if the terms of the series go bigger and bigger as the sum progresses. Well, obviously this is not going to converge. And if it is equal exactly to 1, then this criterion does not give an answer. But in practice, the series for which this is 1 are as good as divergent, because even if they do converge slowly, they are in practice useless because they would be calculating these things on a computer. And I gave you an example in the previous lecture of a horrifyingly slowly convergent series, which a computer simply isn't fast enough or accurate enough in 64-bit precision arithmetic to actually produce with an acceptable accuracy. Okay, so let us pick up a pair of series that we have already seen, one for the exponential and the other for the log, and inspect their convergence. So if we look at the two series we obtained last time, e to the x was a sum, and 0 to infinity, x to the n over n factorial. That was an example of intuitively, right, a fairly rapidly convergent series because the factorial arises faster than any power, and so actually, typically when x is of the order of 1 or thereabouts, this converges to machine precision accuracy in about 17 iterations of that sum. But let us take a look. So our Bn here is x to the n over n factorial. So we would like to find out what is happening convergence-wise. So the limit n going to infinity of modulus. The top part has n plus 1. So this will be x n plus 1 over n plus 1 factorial divided by x to the n over n factorial. Okay, that's the limit n to infinity of. That drops in the denominator, disappears in the numerator, so we have x n plus 1 n factorial over x n plus 1 factorial. Remember, the definition of a factorial is the product of all numbers up to n. So if we have 1, 2, 3, 4, 5, n, and then 1, 2, 3, 4, 5, n plus 1, clearly most of it will cancel, and we simply will have n plus 1 in the denominator. The same goes for x. We only have x in the numerator as a result of this, so it's the limit n to infinity of x divided by n plus 1. Clearly, whatever the value of x, if it is finite, eventually as n goes to infinity, this will drop to 0, and so this is 0, and therefore, because it's less than 1, the series converges for any value of x. For any x on the real line. Lovely. So that's an example of an extraordinarily well-behaved series. Exponential is really quite useful. And this particular series is used a lot in numerical calculations. Let us, however, take a look at our misbehaving model. What is going on there? So the second example, our log x was a sum n from 1 to infinity minus 1 to the power n plus 1 over n x minus 1 to the power n. In this case, the b is the nth term of that series minus 1 n plus 1 over n x minus 1 to the power n. And so when we set up the limit, we will have numerator and the denominator again, limit n going to infinity of minus 1 to the power n plus 2. Remember, we have bn plus 1 in the numerator, divided by n plus 1 times x minus 1 to the power n plus 1. This is our n plus first term there. And the nth term in the denominator will be minus 1 to the power n plus 1 divided by n times x minus 1 to the power n modulus. And, well, quite a few things cancel or disappear here. Let's take a good look. Firstly, because we have a modulus on this, it doesn't really matter which power of minus 1 we have in the numerator and the denominator, so we can just ignore it. Secondly, most of the x minus 1 cancels, so we have one instance in the numerator, and that's it. So we can rewrite that limit and go to infinity of n in the numerator, n plus 1 in the denominator, and then x minus 1 that is left. Just power 1. Okay, lovely. Well, we assume that x is finite, and so it is just a constant multiplier. We can take it out of the limit. So that is modulus x minus 1, limit modulus n plus 1, and going to infinity. When n is very large, 1 can be ignored. That's a limit n over n is equal to 1. And so the thing is x minus 1. Okay, so that is the limit of our ratio, and the series converges when that is less than 1. Okay, you have all seen inequality relations with moduli at school. You may remember they are not straightforward to solve, but in this case they can simply be solved by philosophy. Okay, so if we keep increasing x, when x is equal to 2, this will be equal to 1, right? So our x has to be less than 2. And if x goes into the negative, when x is equal to 0, that's equal to 1. And when x becomes less than 0, this becomes greater than 1. And so that's basically it. Right, this is our convergence radius for the Taylor series. When x is within this interval, the ratio test is satisfied and the series behaves itself. As soon as x is outside this interval, because of that consideration that individual terms must decay, and the next one must always be smaller than the previous one, we have a problem. And this explains why that picture in your handout showed good behavior between 0 and 2. And as soon as we went out of that interval, even if we add further terms, the approximation will become worse and worse. In fact, if the sum becomes longer, the approximation will not improve, it will deteriorate. So it will deteriorate this side of the line, and it will improve that side of the line. So this particular series has, as it were, a best before date or a best before interval in which it works, and an interval in which it absolutely doesn't. Right, so that's the ratio test, and using it, as we've seen in these two examples, is fairly straightforward. You just construct this ratio, take the limit, and you can see how a lot of the previous mathematics I had taught you comes simultaneously into play here. We needed derivatives in order to construct the Taylor series. Now that we have a series, it turns out to be an explicitly defined sequence, and that sequence converges as a result of some limit condition on its terms, and so this is why I've been teaching you all those things at the very beginning. There is another test related to this one, which I will only mention. I will neither derive nor I will use it. Not derive because we don't have enough time, and not use because it's actually considerably harder to use than that one. It's called the root test. So series, the same thing, and the n converges if the limit n going to infinity of nth power root of the modulus of Bn is less than 1, and diverges if it's greater than 1. You can see why I don't want to actually go and use it, because with our limited experience of limits, no pun intended, we've only had one lecture and one workshop there, computing the limit with respect to the power of the root isn't going to be straightforward. Mathematics students in this department are using this a lot because they know how to take such limits, but we will only mention this here and just leave it hanging in the air. It exists. Sometimes it gives the answer when this doesn't, so when this is equal to 1, this might be greater or less than 1, so slightly more information is provided if we're doing post-tests. There is one practicality that is important in using all of this. Digital computers, the standard double precision arithmetic is 64-bit accuracy. This in practice means that a computer can only represent 16 decimal places at best, when the number is around 1, and fewer if the number is very big or very small. And therefore, a computer might not be able to sum the series that are convergent very slowly, because the necessary accuracy is just not achieved in a reasonable time. In practice, this means that if the series converges slowly, there's no point even trying to use it in practice, except perhaps for some pure mathematics sorts of proofs. So the series like the exponential is really useful, but the series like the log is in practice not useful at all. So it doesn't just matter whether it converges or not. It also matters how rapidly it does, although that's a secondary consideration, unless you are professional at doing things like computational chemistry. Okay, so this is series, and let us now move to the next topic on the agenda, and this is interpolation. This is again to do with polynomials, but slightly from a slightly different side. You all remember, hopefully, our shenanigans with least squares, when we had some function measured at some point. This is our xn, and this is our yn, and we perhaps have some points scattered in the space, and then we had fitted a curve to perhaps a linear curve. This is always the best way to proceed. If you have your data and you have some model for your data, so as data, and that's model, that is an equation that has been extracted from some physical considerations, given what we know about the system, that's the best way to proceed. Occasionally, however, the model might not be available, and so we will get some function for something that is utterly unknown. This is x, and this is y for x. However, that something is measured with very high precision. That is, this scatter is absent. And so we have some points that are known a priori to be points that lie on a smooth curve. That, I would note, is a rather significant assumption. Normally, experimental data would contain noise. If you type such data into Excel and tell it to connect it with a straight line, clearly the lines that we would obtain in this case would just be silly. And if you try to connect it with a smooth line, the line will be even sillier. This is why we frown upon data linkage in the plots, where the linkage would simply be representing the noise in your experimental measurements. On occasion, however, from extremely precise instruments, the noise is negligible, and so we can say, yes, we know a priori that these are connected by some points. And these points may be very expensive to extract, or they may refer to historical measurements where we do not actually have anything in the middle. And then the question is, okay, we would rather like to know the value of the function at that point. X question mark, which is in between the points we have previously measured. Or equivalently, we would like to know some other property of this function, like the derivative. Again, perhaps at the point for which wasn't available in the experimental measurement. So df by df. Well, clearly it's not possible to just differentiate a cloud of points. So what people do instead in such cases is they find a suitable function parameterized in such a way as to pass through these points, and then they inquire about intermediate values of that function, or differentiate that function, or do things to it. Such a function is called an interpolant. And today is about polynomial interpolants, which are actually quite straightforward to formulate and obtain. Imagine that we would like that to be the case. So we measured a few values, y of xn is. We know the y's, we know the x's. And so it is yn of xn. We would like it to be a polynomial. Sum, maybe I should number these points with a k. Sum over n, from n0 to, I would not yet specify what it is to, because we will have to philosophize a little bit more about it. And then it will be a n x to the power n. Let's think about it. We know our values for the y, and we know our values for the x. These are our experimental points. For example, x0, y0, and 1, y1. That's just a table of numbered values that we have. And so what is happening here is yk is a sum over n, a n x k to the power n. And then we have multiple such points. So they'll go from k equals 0 to perhaps some big number k, which is the total number of our. I've introduced rather a lot of new notation here. Let us slowly take a look at this equation, because indices have suddenly proliferated and you are seeing indices in an unexpected location. That's just our polynomial. We know that if we manage to find such coefficients, this polynomial, when it is calculated at the case experimental point, we know what it is, perhaps concentration or something, but in the case experiment, must produce kth value of the corresponding concentration. So far so good, and if we knew the function, we would have obtained kth. But we have conducted multiple experiments. K equals 0, k equals 1, k equals 2, perhaps the sequential days, right? So k might be numbering the days on which we have recorded the experiment. And so we actually have a system of equations with respect to k. So one equation for k equals 1, another equation for k equals 2. That's the notation for it. So the same way as you make a sum over an index, you can have a system of equations over an index. And this simply means that there are multiple equations from k0 to some number of experiments that we have conducted in total. All right. What can we do about this? Well, actually, this is a very simple system of equations, because with respect to the coefficients that we would like to obtain, it's actually linear. If it were 2 by 2, it would have been trivial. We know the y case, we know the x case, get the calculator, raise it to n's power. What we are looking for is to extract an. And we can always solve a system of linear equations for an to just obtain them. So, simple linear system. But it is, as you know, not a good idea to have more equations than you have unknowns. Well, actually, it's not a good idea to have fewer equations than you have unknowns. It is a slightly better idea to have more equations than you have unknowns. But in this course, we are not touching on such systems. For your purposes, ladies and gentlemen, you need to have exactly as many equations as you have unknowns. And so if we have k big plus 1 experimental points, so this is k equations and then another one with k equals 0, we must have exactly the same number of unknowns in here. And so this index runs from n equals 0 to the number of data points that we have. Then the number of experimental data points will be exactly equal to the number of the unknowns that we seek to obtain, and this system will be well defined. If the system is overdetermined, the interpolant becomes an approximation, and if the system is underdetermined, the interpolant doesn't exist, at least to that order. So our job is to solve this. Now, thankfully, that's been done. The biggest difficulty here is, of course, the dimension of the system is not specified. If we knew it's 2 by 2, we could solve it. If we knew it's 3 by 3, we could solve it. But the system is k by k, where k is a variable. And so we don't have the methods for doing that. And again, without a derivation, and we will provide these expressions if we are ever to examine them, Joseph Lagrange found a solution for this. So y of x, Lagrange's interpolating polynomial, is a sum over k, the value of the function at our points. So just a point yk really here, times Lagrange's coefficients, ck of x, where these coefficients are the following horrible expression. It is a product, and again, this is new notation. Let's just stop and look at it for a while. Remember sum? Sum over m a(n) was a0 plus a1 plus a2, and so on. Product over m a(n) is predictably a0 times a1 times a2 times so on. Two types of shorthand notation in mathematics. There are also things like product integral, but I haven't told you about that yet. Okay, so that's a product over m that is unequal to k, x minus xm, and then So far, so obscure, and it becomes clear once you start using this in practice, in which case you simply use it literally, and upon a closer look, this isn't actually all that hard. xm are your experimental data points. They are x0, x1, x2, but it is that is on your x-axis time concentration, and so on. So this you know, this you know, this you know. This is just table data. X is our variable with respect to which the polynomial is nothing special, and yk are just the y-axis values corresponding to xk, absorbance, NMR intensity, infrared intensity, whatever it is that you've measured. Okay, so let us go through an example of this where somebody has gone and measured us a function at 3 different time points. They told us that when they measured it in the past, at time equals -1, they have obtained the value of 1/2. When they measured it at time 0, the value was 0, and when they measured it at time equals 1, the value was 2. And it's been a long and extensive measurement, and the equipment no longer exists, and the student has left the project because he hated every moment of it, and we'd really like to know the value of this f for time equals 1/2. And what is the most consistent way of doing that? Well, dust off Lagrange's old book and do that. Let us now just collect the variables. Our x1 is -1, our x2 is 0, our x3 is 1. These are the 3 values of the argument. The corresponding function f1 is 1/2, f2 is 0, and then f3 is 2. This is enough to write down the general expression with the C case, so let us do it. Our f of x is, it's a sum over our experimental points, so let's take a look at the first one. f1 is 1/2, so it goes in here, that's our y, 1/2 c1. Then the next term is for k equals 2, f2 is 0, we just skip it because it will be multiplied by 0. And the third term is the one where k is equal to 3. So the value of the function, in our case is not y, it's f, goes in front, 2, and then c3. And c1 and c3 are functions of x, and they are here. So the next step is to find out what they are. Okay, C1 x is Lagrange's expression, a sum over all the m that are not equal to 1. So m can be 2 and it can be 3. Okay, that is x minus x3 over the k and the m. And note the product. So our k in here is 1. K equals 1. So x1 minus again x3, and this is m equals 3. The other term in here is m equals 2. So we will have x minus x2 over x1 minus x2. This is m equals 2. And you can see why m equals 1 has to be skipped, because that would have corresponded to a 0 denominator. Okay, that's our C1. and we can just substitute the actual numbers into here. x3 is 1, x minus 1, x1 minus x3, minus 1, minus 1, minus 2, times x minus x2, x2 is 0, just x, and then x1 minus x2, x2 is 0, x1 is minus 1, minus 1, so this is x minus 1 divided by 2. The second Lagrange's term, C3 of x, okay, in this case, k is equal to 3. So m can be 1 and it can be 2. X minus x2 over x3 minus x2 times x minus x1 over x3 minus x1. This is for m equals 3, this is for m equals 1, now m equals 2 here. So both m's that are not 3, as per the instruction in that product here. Okay, substitute the numbers in. X minus x2, x2 is 0, just x over x3 minus x2, 1, times x minus x1, x1 is minus 1 plus 1, over x3 minus x1, 1 minus minus 1, 2. So x plus 1 over 2. And now the final thing is to substitute that into the expressions that we have there. Our f of x is 1/2 of C1 x minus 1 over 2 plus twice the C3 x plus 1, and optionally we can just tidy this up by opening the brackets, but I probably wouldn't bother. So x minus 1 over 4 plus x plus 1. That's our interval. And let us now test it. This is quite important to make sure that the function we have obtained actually does pass through the points necessary at the values of the x that we have. Now I need to remind you that all arithmetic in my head goes through Russian, and so it is entirely possible that I've lost some coefficients in there. So it would be embarrassing if they now don't fit, but not perhaps entirely unpredictable, and if they do fit, we will be fine. Okay, it is clear that x2 actually is a match. Right? So f of x2 is obviously 0 if you put x0 in there. So that works. So far, so good. Let's try the x3. F of x3. If we put a 1 into here, we have what? We have x minus 1, 0, so this term disappears, and this is 1 times 2, it's actually 2. Good stuff. And then f of x1, so minus 1, this will be minus 1 here, minus 2 here, so that's a half, minus a half. And then that's minus 1, and that is 0. That worked. So with just a minus for some reason that we need, and I think that's, oh no, we don't actually, because the x is minus 1, it is minus, yeah, it works. So I didn't actually make any arithmetical mistakes. Good. And the final thing to do is to actually do what we were bid, and to calculate f of 1/2. And if we do the substitution and then do the arithmetic, it's 11/16. And under the circumstances when this is historical data and no further measurements are possible, this is in practice the best way to proceed because the interpolated data. Notice also that this interpolant is quite handy in many respects. If we were told to find what is the point of the maximum or minimum of this, well, it would not have been possible to actually judge that from just 3 measurements there. However, interpolant is an analytical function which we are at liberty to differentiate or integrate and do things to it, and so we would have been able to find the minimum or the maximum. Okay, so far so good. There are 2 words of caution that are attached to interpolation methods. Here, one is never use the interpolant outside the point cloud. Let's say you have some points there, there, and you have created a nice, neat-looking interpolant that passes through all of them. And then somebody tells you, well, okay, what about the x that is somewhere around here? Well, bad idea, because this interpolant is a polynomial for the same reason as our Taylor series blew up when we went out to very large numbers. Any interpolating polynomial will do exactly the same. And so if you are asked for a point in between your existing points, you are probably okay. Still iffy, you have to be careful, but it's okay to interpolate in between. Extrapolation with polynomials like that is not a good idea. The second thing that you have to worry about is something called Runge's instability. You will notice shortly after Lagrange published this that the following phenomenon tends to occur. If we have a great number of points, like something this kind, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then if we go through the motions in here, we will get a polynomial of the order 9. That is 9 powers of x and the little term in front. If we plot it, however, what we discover is that the plot looks like this. Technically speaking, like a gin out of the proverbial bottle, it did what was required. It created a polynomial that passes through every point. However, it's quite obviously not what we were looking for. What we were looking for is something like this. Now, this is called an instability, named after a mathematician called Runge. And it simply says that interpolating polynomials of order greater than 4 are not a good idea. So power less than or equal to 4 is something that is useful in practice. As soon as you exceed that, you start getting these instabilities. So how do we deal with situations where we have so many points that the degree goes very high? We interpolate them piecewise. That is, we say, let's take, for example, these 3 points and do a quadratic interpolation between them, like that. And then we take those 3 points and do a quadratic interpolation between them, like this. And so on. If we take them in groups of 3 and do quadratic interpolation, or groups of 4 and do a cubic interpolation, this is called a local interpolant, and it will always be stable. It's actually possible to augment those equations to make sure that it's not just the value of the function that links up, but also first and second derivatives, in which case this is called a spline interpolant. You must have heard about spline curves somewhere in computer language context where they're used in computer graphics. But basically interpolation of large data sets by polynomial methods always happens piecewise. This is what happens inside Microsoft Excel when you tell it to connect your dots with a smooth curve. If memory serves, Excel employs a really ugly piecewise quadratic interpolation, and you can sort of even see sometimes that the curve looks very artificial and not at all physical. So avoid that when you can for these reasons, and if you do know a priori that your data is free of noise, then you can do this interpolation. Okay, so the summary of the lecture is we have looked at how and when polynomial approximations go wrong. So Taylor series have a convergence radius. You are lucky if it's infinite, like for the exponential, but in most cases it's finite. And using it outside the convergence radius is guaranteed to lead to problems. So be careful when you do it in practice, and rest assured you will in your third course here or in your actual activities for research. And then in situations when we would like to know the value of the function in between the points where we've actually measured it with some reasonable guarantees of accuracy, then we use interpolating polynomials, and it's just writing down the polynomial and then solving the system for its coefficients. And but one particular method of doing that is called Lagrange's method. Quite a bit of path, as you can see, and these equations would obviously be provided if we ever require you to do that in the examination. Be careful about not extrapolating and not using interpolating polynomial powers, because you'll have plenty of practice at the workshop. Any questions?